All the sorting algorithms we're talking about, we're imagining are done in a computer. All right, so that's our model of computation. We're counting comparisons, or we're counting machine language instructions, or some proportion of those things. We usually don't care about constant factors, so whether we just count comparisons or other kinds of instructions, it won't matter so much. It usually just doubles or triples the number. We want to get an asymptotic sense of how fast the algorithm works, and we'll do that today. But every time we have an operation, it's some kind of computer machine operation, moving some piece of data from here to here, looking at some piece of data, comparing two pieces of data. The issue of how to do a problem when you have a different model of computation is a really much broader problem. I mentioned yesterday this idea of trying to model computation biologically, trying to connect a problem by encoding it in some sort of DNA, letting the biological process go its own way, and hoping that you've encoded it so cleverly that the biological process actually describes an answer to the problem you encoded. That would be a really cool area of research, and it is a cool area of research. But here's a simpler version of that where I don't have to spend 2 hours actually giving you details. Let's say you want to sort some numbers, and we're going to do it like this. Now, this is really meant very lightly, so don't take it so seriously, but it's just to give you a sense of this. Here's how we're going to sort a bunch of numbers. We will have the person who's giving us the numbers, instead of writing them down on a piece of paper, they measure them out on pieces of spaghetti, okay, and cut little hard pieces of spaghetti out. So each piece of spaghetti is the length of the number you want to sort. And then you have this machine that gathers up the pieces of spaghetti like this, wraps them up in a big rubber band, and goes boom, smashes them down on a table so that they all fall down to a flat table. And then this little laser beam comes down, and the first piece of spaghetti it hits, bing, that's number one. Bing, that's number two. And the laser beam goes down to the bottom, and you sort all the pieces. Right? How long does that take? Well, I'm not asking for an answer to that question because I want you to just think about it. I mean, what does it mean to measure the speed of that algorithm? Is that an algorithm at all? How does it connect to the stuff that we're talking about? It's just something to think about. All right? That's the spaghetti sorting algorithm. Boom. All right. Questions before we get started? Teresa.
What does in place mean? You talk about it in the book.
Yeah, in place means that usually when we're sorting, we're imagining that the numbers are stored to begin with in some array.
Okay.
In place means that you're only using a constant number of extra storage locations. That you don't need to have another blank array for moving things around in. So in place means don't use any extra space. Okay, we did spaghetti sort. Now we're going to do bubble sort. One more time, after I explain how this sort works, we are going to write code for it. We're going to do this for two reasons. Number one, I want to make sure everybody can do it. Number two, because Todd pointed out that I think I have a little mistake in my code here, and we're going to find it together and make it an exercise rather than just a small correction. I have a less than, and it should be a less than or equal. But we'll double check and make sure that it really should be a less than or equal, and use that as a good exercise to bridging the gap between me making a description and you being able to write the code. And like I said, I am going to fade with this kind of stuff soon, but I think right now it's really worthwhile. So before we write any code, code is a perfect thing to look at if you want to just let your brain go blank. So it's better to understand how the algorithm works. Then look at the code. All right, here we go. So I'll just make up a list of numbers here. That's enough. All right, 15, 13, 2, 11, 6, 5. And they go in order, an index from here to here. So this is index 1, 2, 3, 4, 5, 6. We want to sort these numbers in ascending order. So when we're all done, 15 should be in the bottom, 2 should be in the top, and it should all be sorted. And here's the way bubble sort works. And you'll see why it's called bubble sort in a minute. What it does is it goes through a number of what I'll call bubble phases. And in each phase, it lets the lighter elements bubble up, like bubbles in a pool, and the heaviest element sinks to the bottom. In each phase, the heaviest element will sink to the bottom, and the ones that are lighter on top of it will, in some sort of an unpredictable random way, bubble their way up. Not necessarily to any particular place, but just above that heaviest one. Okay, how does it do that? It does it in a really, really logical way. You start at the first two elements, you compare them, and the bigger one will go to the bottom, and the smaller one will go to the top. So you'll exchange them. So it looks like this. That's so far. And then you continue shifting down one spot, comparing the second now with the third. and you switch them if necessary. So now it looks like this. And now 15 with 11, 15 with 6, and 15 with 5. So in this case, 15 just sank to the bottom and everything else bubbled upwards. What's going to happen in the next bubble phase? Who can read off the numbers? John, can you do it?
Well, 13 will go down to 2.
Okay, and what does it look like on top of that?
2, 13, 11.
Okay, but we're going to do the whole thing at once now.
Well, 2, 11, 6, 5, 13.
Right, exactly. So I'm just going to make a little box here to show that that area is already sorted. Okay, 15's right, 13, 15's right. The next bubble phase, 2 and 11, that doesn't switch. 11 and a 6 would switch. The 11, 5 would switch. So it looks like 2, 6, 5, 11, 13, 15. Okay, Donna.
Does the algorithm know enough not to keep comparing down?
It does when we implement it. We'll have to do it carefully. It won't if we don't tell it to. We'll have to do that. It's a good question. Right, Donna asks, does it know enough not to go past this little mark that I made? Right, it's pretty darn stupid to compare 11, 13 only to say, oh, I don't need to switch those. It should know it doesn't have to switch those. We should have some way of stopping it at this point, and we will. We'll put that in. That's one of the features of bubble sort, even though it's an n-squared algorithm, is that it does tend to stop early if things are well sorted, and you'll see that too. In other words, what if I was really lucky and the whole thing was sorted at the beginning? What would have happened? It would have gone through and not made any changes at all. If you go through a whole bubble pass and you don't make any changes, then you shouldn't go through another bubble pass again. And we'll incorporate that in the algorithm as well. So that guarantees the algorithm will run in linear time if it's actually sorted virtually almost when you start. All right, the next stage, the 6 and the 5 get changed, and now it's sorted. We'd have to run through one more time because I think you have to run through as many times as you have elements minus 1. Because if the biggest and the second biggest and the third biggest and the fourth biggest and the fifth biggest are all in their correct place, then you know that the smallest has to be in the right place too. There's only one place left for it.
Does it stop when it doesn't do any switches, though?
Yes, we're going to stop. The thing about stopping when it doesn't do any switches, we have to go through a whole pass, not do any switches, and then we know not to do it again. So if we actually have one left, and on the last one you didn't do any switches, then you don't save anything. Okay. Let's go ahead and write the code for this. Let's not just, it's right here it's 4 lines in the notes, but let's go ahead and write it as if we didn't know how to write it. How would you design it? You can always design things depending on how you think of them, right? You can think of them inside out or outside in or top down or bottom up. Everybody's got their own style, and I'm not going to force you to think in any way. But the way that I like to think of doing this is, well, it depends on the day. Sometimes I think of doing it from the top down, sometimes from the inside out. Let me hear some suggestions. What do you want to do first? You want to code the bubble phase first, or do you want to do the big picture first and put the bubble phase in when we need to? There's clearly 2 parts here, right? There's a bubble phase that gets done many, many times. There's an outer and an inner. Who's got an idea? Who's got an idea? Blake, you didn't have an idea because you're not raising your hand, so give me one.
I guess there should be some loop that goes either through the number of elements or until there are no switches.
Okay, is this loop meant to be the one that counts the number of bubble phases or that actually does a bubble phase? Because doing a bubble phase will need a loop too.
What exactly do you mean with the bubble phase?
The bubble phase is the thing that compares adjacent elements and shifts down like that. So you want to do that loop, or you want to do the loop
I was thinking
the loop on the outside? Okay. The loop on the outside has to go how many times? I think you just said it.
either the number of elements or until there are no switches.
Okay. Either until there's no switches, but we'll put the no switch part in later. We'll just do until there's no more elements. So that means n minus 1 times. Because by that time, you know the last one's in the right place too. So here, I'll write this real pseudo. For I equal n 1 to n minus 1. It's going to do it n minus 1 times. What's it going to do 1 to n minus 1 times? It's going to do this bubble phase. How do you do a bubble phase?
Another loop, it would go from...
Let's do it really simple. Let's assume we don't stop at these bracketed points.
It would just be from
I equal Well, j equal
1, 2, and minus 1.
starts here, goes down to the second to last one. Okay? And then inside this loop, we need to compare the jth element to the j plus first element. It looks something like this. If a brackets j is bigger than a brackets j plus 1, then what? Should we swap them then? Swap a, j, and j plus 1. This means we're sending the array and the two indices to the array, and we're hoping they get swapped. And otherwise, we don't do anything, right? Otherwise, we just go back in the loop. All right. So there's the code. I mean, that's it. This doesn't stop at these little marks that I made. It also doesn't check if it's gone through a whole bubble phase and done any switches. So let's put those two things in one at a time. And I think it's pretty straightforward to put them in. This is the first time through the bubble phase. How far do we have to go down? How far does the loop have to go? It has to go all the way until j is n minus 1. It's got to go to that point. Right? The second time through, it goes up to n minus 2, and the time after that, it's n minus 3. So if the first time it's n minus 1, the second time it's n minus 2, the third time it's n minus 3, the fourth time it's n minus 4. So the ith time we do it, instead of it being n minus 1 every time, it's going to be n minus I. So if you look in my notes, I have a strictly less than n minus I. And that's wrong. It should be less than or equal n minus I. So it does go up to n minus I. That's a mistake. So this is a little better. We'll analyze the complexity of these two in just a second. Let's say we don't add any more features. Let's say we left at n minus 1. What would the complexity of this algorithm be? Two loops, one inside the other. N minus 1 times n minus 1. That's order n squared. Now, it looks like it's a little better, but you should all know that it's not that much better. Just because we've got this I in here and the inner loop goes a little bit less, that doesn't mean we're going to get out of the n squared world. What happens now is, the first time through, we have n minus 1 steps. The second time through, n minus 2 steps, etc., all the way down until the last time where we have 1 step. And you all know how to add up these numbers. God knows, you must have seen it a dozen trillion times. These are triangle numbers, right? And they come up all the time, especially in these double loop kind of situations where the inner loop is based on the outer loop. And this is, you can add it up in particular, but as far as the big order complexity goes, it's big theta n squared. Okay? Questions about this so far? Let's do the last thing in bubble sort then. Let's throw in the part that does the check to see if the bubble phase didn't make any switches. So we're going to need some sort of way to remember whether we went through this whole loop and switched anything. Well, when we switch something, we do it here. So if we swap it, I'm going to say a switch was made, and switch equals true. Now I have to use that information. Where am I going to use it? Which loop needs to use that information? The outer loop has to decide. It's going 1 to n minus 1, but it only wants to do it if the switch is true. So for I equal n to minus 1 and switch is true. Well, that's OK. Everything's OK so far. What should we initialize the switch to, just to get it started? It's got to start out as true, so it actually begins. Well, now it's always true. So what good is that? Where should it become false?
When we start each iteration.
Every time you finish a phase, and you go back to here, and you're ready to start a new phase, and you've decided the switch was true, so you're going to start a new phase, before you begin that phase, you have no idea whether the switch is going to remain true during that phase, so you need to reset it to false at the beginning of each phase, right here. Switch equals false. So you have a little Boolean variable. You keep track of it. In one place, you initialize it here before each iteration of the loop, and once on top just to get it started. Are there questions about this? Doug? Yep.
I mean, yes, we might save a couple times of going through the loop, but we're also adding
a Boolean set every single time. How?
Good point. Is it worthwhile to do it? Is it worthwhile because you might save a couple passes through the bubble phase to add in an extra line here, an extra line here, and an extra line here?
Well, if you've got a billion numbers, we can finish it after 10 passes. Yes.
Right. Right. So how do you know? So let's just say, let's say, here's an example. Let's say somebody's got a big data structure with a huge file, and it gets messed up every day, and it's got to be resorted, and they don't have any better way to fix it other than resorting it from scratch. But they know that when they use bubble sort, practically, they can't analyze it, they can't do any distribution, but they know that it tends, even though they have, like he says, 100 million records, that it tends to sort after, the 60th thing, that only 60 things got out of whack. So then I think it is worth it. It's an engineering question and not really an analysis question. Because none of this helps get rid of the outer n squared. All this helps is that if it happens to be sorted, you get an order n best case, which is really just interesting as a point of fact mention about the algorithm, but it wouldn't make the algorithm better or worse than another one, except in particular special types of data. Okay? Other questions about this? So here's the first sort that most people learn. Most people have seen this, I think. Here's another order n squared sort. This is often mentioned. A lot of people say, oh, this is the way most people just sort like cards if they're in their hands, and you're going to have a game of hearts or something and you want to sort things. You hold the cards in your hands, and then you look and it's all a big mess, and you start on the left end and you say, okay, that one's in order, and now you take the next card and you rearrange it so that your first two cards are in order. Now you take your third card and you insert it in that area of the first two where they were in order and put it in the right spot. Then you take the fourth card and look through and see where it goes. Then you take the fifth card and see where it goes, sixth card and see where it goes, etc. Taking successive cards, looking in the left area that you've sorted so far, and putting the new card into the spot that it belongs in that sorted area. That's called insertion sort. And we're going to do it now with an array. And, well, this time maybe we'll write the code this one more time. And then after that, we'll stop. All right, questions about the strategy so far? Let's do an example. All right. So with insertion sort, we're going to go through the thing in phases again. And each time we go through it, we will increase the sorted area from the top to the bottom until we finally have the whole thing sorted. Now, if you want to do it this way, then in your first step, you immediately know that an area of one card is sorted. It's just one card. So 16 is sorted on its own. Now you want to add one more slot to the sorted area. You want to include the second spot. The second spot is a 5. So you pick up the 5 in your mind or in your hand, and you say, where does it fit in the sequence 5 and 16? Well, it goes in front of 16. So the next phase looks like this, and all the other numbers sit there and wait their turn. Now 13's turn. You pick up 13 and you look. Is 13 bigger than 5? It is. So go after that. Is 13 bigger than 16? It's not. So 13 belongs right in here, and the list looks like this. Okay, so far? Next step, 1. You start at the top. 1 is actually smaller than 5, so you stop. You basically take your new number, run through this list from top to bottom, and see which one is the right place to put it in. And then when you find that place, you shift everything down one spot. Make that little mark so that you know that area is sorted, and continue. Here's the number 2. It's going to fit in right here, and these 3 will move down. 1, 2, 5, 13, 16, 5. I'm going to call this 5A and 5B, just so we can keep track of it. Now what happens? What's the last step? What does it look like?
1, 2, 5A,
5B is going to be in front of 5A.
What's going to be in front, 5A or 5B?
5B.
Or does it matter how we implement it? Depends on whether we use a less than or a less than or equal, right?
Or whether we go
or whether we go from the bottom, or whether we go from the top, right? There's a lot of different ways to do it. So I think the answer to my question, where does 5b go, is, well, show me how you implement it first. The way you described it is too vague to really know. So let's just say it does this. This isn't perhaps the best way. But if it does do this, then this sort is what's called unstable. It took two identical elements that were in order 5a, 5b, and when it was all done sorting them, it happened to switch them. Sometimes it's very important that a sort is stable. Sometimes we don't really care. But you should know it's one more thing, like being in place. It's one more thing that you measure about a sort, because sometimes you really need the sort to be stable. You need it not to reverse the order of elements that happen to be exactly the same when you started. Donna?
Can you give an example of why of when it needs to be stable?
Yes, I can.
Okay.
Can you wait maybe till the end of the lecture or till tomorrow's lecture? There's a sort called radix sort, which is a sort that's really cool. It doesn't use these kind of methods at all. And a radix sort needs as a subroutine a sort that keeps things stable. And if you don't keep things stable, the sort doesn't work at all. And you'll see it tomorrow. So yeah, that's a great example.
Another reason would be, say you're sorting something by title and author. And you sort by title and everything's in title order, and then you sort by author, and you want to keep everything in title order within the same author.
I'll just ask Chris next time.
You want to give Chris advice?
What Chris said is fine. Actually, the example in radix sort is the same exact idea, except that it's digits instead of titles and authors. But Chris is right. On the internet all the time when you sort things, it's already in order one way. You want to sort it the other way. You don't want the order of the first way to change. Right. Good, Chris. Don't let Donna beat you up there. All right. So how do we do this? Do we go from, when we do the insertion, do we start here and go from top down? Do we start here and go bottom up? Right? We can do the insertion looking from the top, looking from the bottom. And once we find out where it belongs, what do we do then? How should we do this? How should we actually implement it?
Linked list.
All right, Neil, give me an idea.
Linked list.
A linked list.
So I can insert it.
Oh, I see. That's a good idea, because a linked list, you can insert things in the middle and not have to do the shift down. And in fact, that's a cool variation, but that's not the way it's normally done, because you can do it in an array without worrying about the shifting. You just have to, well, you have to worry about the shifting, but you can do it in a relatively efficient way. But your idea is a very good idea. You could do these things in a linked list. You could try to do it that way. Do we have a way to do it in an array?
What you can do is pick up the element that you want.
All right.
From bottom and go out.
If I pick 2 up and I compare it to 16, 2 is smaller than 16, then what, Sean?
Put the 16 into the space that 2 came from.
Okay, so if I go from the bottom up, then I can take care of the shifting while I am doing my comparing. I compare 2 and 16, and if 2 is smaller than 16, I just shift 16 down right away and move 2 up. And then I can compare 2 against 13, moving 13 down, 2 against 5a, moving 5a down, 2 against 1. It's not smaller. I just leave 2 there.
That's a bubble sort. First cousin to bubble.
It looks a little like bubble sort, but it's not exactly the same. It doesn't do the exact same order of comparisons, but it should remind you of that. There's another way to do it. You can kind of go through comparing 2 to each of these spots and stopping at the point where you find out it belongs. So we run through and we find out that it belongs here in index 2. And now you have another loop that just goes from here and copies these things down. Boom, ba-boom, ba-boom, and then moves 2 in there, rather than doing it as you're comparing. It's the same idea, but what does this remind you of? This should remind you of something. Right, it should remind you of that Same game, right? The idea is that you're going to work from the bottom up, moving things into the blank that you know must be, and then fitting your thing into the blank spot. It should remind you of that. It's a little bit similar. All right, so should we write the code for this? The code's in the notes, or do you want to move on? I'm leaving this up to you. Do you feel it's useful to write the code, or should we move on?
It's also in the text.
Oh, yeah. There's a whole big section in the text on this. Yeah.
I do have a question. How would you get 5b ahead of 5a? What do you have to do to make that?
So over here, when we're moving our way up, and we're deciding when to stop, we're having a test whether this is bigger than or equal to this. Okay, if it's bigger than or equal, then we're not going to move up any further. So if we do it that way, where the ones in the bottom are bigger than or equal, then they'll stay here underneath 5a. If we check if they're strictly bigger than, then it'll end up going one more step before it does it. So if we're going from bottom up, we'll have to use bigger than or equal to make that work, to make it
Also,
stable.
if we started from the top, we could get it on top.
Right, you could.
The same reason that it would be on the bottom if we start from the bottom.
That's true. That's true. And in fact, there's no reason why not to go top down. You can go top down here too, find the index that you're up to, and then do the same thing, just shift things down. Okay. Questions about this one? So what's the complexity of this? We're doing something as many times as n minus 1 elements, because each time through, we add one more element into our sorted area. And we started with the beginning of the first one in our sorted area. So there's n minus 1 more to go. So n minus 1 times, how long does each step take? Oh, they all take different amounts of time. The first step, yeah, Andrew?
So that doesn't take into account the shift.
Not yet. We're going to do that right now.
All right.
So we're going to do n minus 1 phases, but each phase takes how long? How long would this first phase take? To take 13 and compare it up here and then do the shift? What would it be? What's the worst number of steps? We'd have to compare 13 to 16 and 5, right? And then we'd have to shift down possibly 2. The shifting is going to, at worst, double the comparison, right? So that's not going to be too bad. So the first phase, we have n minus 1 phases. They're not all the same, so we can't do a multiplication. The first phase is going to take 2 steps, possibly times 2 if we count the shifts. The next stage is going to take 3, possibly times 2. The next stage will take 4, all the way up to, I think n minus, we need n minus 1 of these numbers.
N minus 1, but why wouldn't you have 1 as the first stage?
Oh, we do have 1 as the first stage. I'm sorry. Right, 1 to n minus 1. I missed the first stage. You have to compare 5a to 16. I started over here too early. So this is the same sum we had before. There's n minus 1 terms from 1 to n minus 1. We add them all up together. You get order n squared. If you multiplied it by 2, you just get 2n squared. So that's still order n squared. So engineering-wise, it might be slower to have to do all these shifts. It probably is slower than bubble sort. But as far as the order of complexity goes, it's still order n squared. Make sense? Andrew, is that, you're clear on all that? You had a follow-up or no? Okay.
I have a question.
Tony.
Would there be any reason not to do a data structure that was both an array and a linked list? That is, an array of node objects that pointed to each other. If you had that, you would know what you hadn't inserted, and you could use the linked list for the insertion process. Thereby, you wouldn't have to shift, except when you got to the very end and needed to copy it into a new array.
So Tony's following up on Neil's suggestion of doing this without an array, doing this with a linked list.
No, both. You use both. But you need to know the order. A linked list requires you to walk, to put it down the list, so to speak.
Right.
If you had an array of linked list node objects, you wouldn't need to do that.
But we can't have both advantages of both, because if we go ahead and delete something in a linked list and move the arrow to here, then going from here to here is not going to be a one step in the array anymore. Right? So
The thing is, you're using, in my suggestion, you're using both. You're pointing with the linked list so that you'll be able to walk down the list later and copy it into a new array, so everything will be in the proper order.
oh, I see. So you can have a linked list that you use for these insertions, and then you copy that linked list over to an array to do the finding later.
To
You could do that.
What your linkage actually ends up being.
You could certainly do that. It would save you this factor of 2, but it does require the copying over, which kind of adds that factor of 2 to some extent back. And I don't know how it would compare practically if we actually ran it, but it still ends up being order n squared. It doesn't save anything there.
That's not a factor of 2 anyway, it's a factor of 3,
3 operators.
Actually, we're not doing swaps here. We're taking say we decide we want to take 5b and stick it here. Then we take 16, move it here, 13, move it here, 5a. We just copy over. We're actually not doing swaps. The way to do it fast is go up to 5, move 5b up to 5a where it belongs.
How would you do this? How would you do reverse 5b then? If you copy 16 over 5b, where is it? Yeah.
You copy it to some other place somewhere.
That's just another
That's just once. You just do it once. You do it one time at the beginning, you move all these down, and then you put 5b in at the end. You don't swap every single time through. Right? It's like a big, long cycle. You pull one guy out, you shift everybody down once, and put that guy in at the top.
Okay, well, in which case you're doing all that many writes, right? But you're not doing it twice.
You're not doing it twice every time. Just every time you go through up to the point you want to insert it, you do one copy. It ends up not being, it's 2 times 2 plus 1, 2 times 3 plus 1. That's what it ends up being. Okay.
But your point being that those plus 1s and plus 2s.
My point being is that they're all order n squared, and if you want to compare these things, you really have to build the program and run it. Because the only way to really check is to do some engineering on it and not to, you don't want to sit and analyze about the plus 1s because whether your compiler works in one way or another is going to make a difference there. So, questions? Any more questions about this one?
Is this particularly good for some circumstances?
Insertion sort also works well on things that are pretty much sorted. If you look at it, it doesn't do a lot of work on things that are pretty much sorted. It doesn't have to do any of these shifts, for example. And it works very, very fast for very, very small lists. And it's used sometimes if you have only 15 or 20 elements. Instead of using the overhead of a fancy data structure, you just zoom it through on this, and it doesn't take that long. The average case analysis is very much more complex. You have to decide what this algorithm would do over all the possible inputs and divide by the number of them. But that's ridiculous. There are n factorial different inputs. We're not going to do them all. So we want to kind of divide them up into classes. And the way you do that in insertion sort is kind of very natural. Basically, you assume that with a random distribution of the numbers, when it comes time to do the next insertion, you might get lucky and do the insertion right away, or you might get unlucky and have to go all the way back to the top to do your insertion, and that any of those places are equally likely. That's a way to divide it up into classes of equally likely possibilities. So the analysis goes, let's consider each of those possibilities equally likely at every interval, add them all up as to how many steps it would take, divide by the number of possibilities, and you get a result. And the book does this in gory detail, and it ends up being something like this. That on the average, it does a factor of 50% better, but still order n squared. So the average case analysis for insertion sort doesn't make it any faster. It happens to actually run twice as fast in the average case, but no more than that.
Which is intuitively what you would have said.
Yeah, well, intuitively what you might have said, but yeah, it is intuitively what you might think. And you should realize that this might make a big difference for small values of n, where twice as fast is pretty darn fast, and you don't need anything fancier than this.
What algorithm did they exactly use for that average? Because it seems like, for example, if we wanted to, when we go to look to see how far it is, we find out the midpoint of the already sorted array. And if it's larger than that, we go down, and it's smaller than the midpoint, we go up. It seems like something like that would
to use
the insertion sort, but it would.
You want to use binary search to do your insertion sort.
Something like that.
Yeah, that sounds like a problem I asked on the problem set. Did I? I should have if I didn't. I think I did ask that problem in the problem set. Or on some problem set. Everybody puts that in a problem set. It's a really natural question, and it's a good thing that you thought about it.
Okay.
It's a very natural way to do the problem. Why bother looking up linearly for the place to do it? Why not go ahead and do a binary search to find the place? After all, this is sorted. Let's take advantage of the fact that it's sorted. A binary search will cut through this in log n time instead of n time. We'll find the index where to put it in a flash. In fact, it's such a good idea that your first gut instinct will be, hey, it's not n squared anymore. It's n phases, but each phase only takes log n steps to find the spot now. It's a really good idea. It'd be n log n. It isn't, though. So why isn't it? because you still have to copy everything down. You can find the spot really fast, but there's no fast way to copy everything down. So now we might be able to leverage Tony's idea and Neil's idea of having linked lists. Because if we had linked lists, then we could copy the stuff down fast. Then we could just break a link and reconnect a link and move everything down rather than to have to shift everything. So maybe we could combine a binary search idea with a linked list. But the thing is, you can't do binary search on linked lists. So hence Tony's idea of somehow leveraging the advantages of both. But we'd have to think about the details of how to do that. All right. Good points. Good thinking. That's an excellent question.
Thank you, Gil.
That's a really excellent question. All right. Other questions, other points about this?
Some of these sorts just depend on the rank order of the numbers, right? So the other sorts depend on the absolute values that you're trying to sort.
What do you mean by the rank rather than the absolute value? You mean whether they're negative numbers?
Yeah, like if that 16 were 2 billion rather than 16 wouldn't make any difference for the insertion sort, but it would screw up other sorts.
Oh, you mean if this number were just huge?
Yeah.
It doesn't matter in the sorts that we'll be talking about today, but it matters in other sorts that try to take advantage of the size of the numbers. If you know a constraint in the size of your numbers, you can sort a lot faster. What if all your numbers were binary numbers? I mean bits. Lots of zeros and ones. You want to get all the zeros in front. You want to get all the ones at the end. There's got to be a faster way to do it than n squared. In fact, there better be a linear way to take a list of zeros and ones and just put the zeros. In fact, you all should know how to do it. It's the stupid Same game again, right? You got a bunch of zeros and ones. Just copy the ones down to the blank spots. And do a one pass through your array. So,
You mean like a search in a Boolean array?
yeah, a Boolean array, just zeros and ones. And we want to move all the ones to the bottom.
I thought you meant binary numbers.
No. Bits, actual bits. Although, if you can do binary numbers, bits, in a linear pass, and since every number is just a sequence of binary numbers, can't we just like maybe sort on one column, get that in order, then sort on the next column, get that in order? Well, we can, but you got to know which column to do first. It's a little complicated. Actually, that sort is called radix sort. We'll talk about it tomorrow probably, not today. We won't get to it today. How long does that take? N for each column. How many columns are there in these numbers? If you have n numbers, then the size of your number might be log n bits. You get that n log n again. But if I told you all my numbers had at most 3 bits, then how long would that algorithm take? 3n. So if I know my numbers are small, then I can do linear time sorting. But if I don't know anything about my numbers, then that sort idea ends up being n log n. So that's a preview, because you guys are so smart and ask all these questions, but otherwise we wouldn't get to that quite yet. Hence, if you didn't know what I was just talking about, don't worry.
Small relative to the length of the list, is that right?
Yes, small relative to how many numbers are in the list. Constant relative to how many numbers are in the list. If I know all my numbers are bounded, say, by 100, but I could have 2 trillion numbers, then I can do that sorting in linear time relative to the size of the list. Yes, Chris. All right. Let's move on to n log n algorithms. Merger sort. There's no such thing as merger sort. Merge sort. Mergist sort. All right. Merger. Merge sort is the first order n log n algorithm we'll talk about. Mainly because it's relatively easy to understand. 2, you've seen it before. And you've actually seen the code for it before. Nevertheless, I'm going to go through it again. I'm going to talk about its recurrence equation ever so briefly. I'm going to talk about the fact that it's naturally a recursive algorithm to describe it. And then we'll talk about what actually happens when you actually do the recursion, what comparisons get done first. So we'll do this on an array of, say, 8 elements, a nice power of 2. There we go. There's 8 numbers. I'm thinking, if in the last 20 years that I've been teaching, somehow I could reconstruct the list of numbers that I make up randomly like this on the spot and analyze to see which ones get reused, that would be really interesting for a couple of seconds. I just wanted to let you in on what goes on in my mind in between thinking of the next sentence. Yeah, I'm scaring myself too. All right. Here's the idea of merge sort. You get a list of 8 elements. You split them into 2 halves. The first half and the last half. You recursively sort each half. That you get for free. How do you recursively sort each half? With merge sort. How do you do merge sort? I'm telling you how to do merge sort. Okay, but it gets done. That's the beauty of recursion. And thank God you spent a whole month doing schemes, so I don't have to go too much into it, but I will still go into it. We recursively sort these 2. We get it for free. So this turns into 13, 15, 16. I'm so slow. 7, 8, 10, 82. Good. This is sorted, and this is sorted. That was done for free. Here's the glue. Here's what you do once you get them sorted recursively. You make 2 recursive calls at the beginning of your algorithm. Well, at the very top of your algorithm, you check to make sure that there's not just one element in your array. If there is one element in your array, you don't split that element into 2 parts and merge it. You just return the element. But if there's more than one, you split it into 2 even parts, you recursively call in each part, and now you glue the 2 parts together. Here's a dumb way to glue them together. Just connect this to this. Now it's sorted. Well, it's not sorted, right? You can't just do a dumb gluing. You got to do some kind of clever gluing. The gluing that gets done here is called merging. We have 2 sorted lists. We want to combine them together in a mutually sorted list and do it, ideally, as fast as possible. Now, here's where understanding recurrence equations come into play. Because before you decide how you're going to do this gluing, you better have a good idea of what you should be trying for. If you spend a whole day long and come up with an n-squared merging, you should know that that was a big waste of time from the beginning. What's your goal? How fast should you be trying to do the merge to make this n log n? In order to do that, you need to set up what's kind of a partial recurrence equation. The time it's going to take to do this algorithm is the time it's going to take to do it on 2 problems of half the size, plus something to do the gluing. Well, you should have a nice command of recurrence equations to know that if I put n squared in here, that the overall complexity is going to end up being n squared and not n log n. But if I get n here, or something proportional to n, then this recurrence equation is going to end up being solved by n log n. So I got to be going for n here. I got to be going for a time that's proportional to the size of my list. Right? That's why it's worthwhile to know recurrence equations, because it helps you give yourself a goal for your algorithm. Instead of just working randomly and then checking at the end whether it worked, and you decide, oh, I spent 2 weeks doing that and I didn't even know it was impossible. All right, questions? I'm not going to solve it. Ask Mark to go over this if you don't remember how to do it, or go back, look at your notes, or read the book, or any number of things, or ask your friend, or ask me. Let's go back to here. Yeah.
Can that be n log n, the merge part? Is that the max?
No, I think actually if you make it n log n, I think the complexity ends up being n log squared n when you're done. I have to double check that, but that's my guess, and I'm pretty sure that's right. You remember in the discrete math class we did this master theorem, and then there's this version of the master theorem that I gave you in a problem set that if it's a log n off, which isn't enough to use the master's theorem, that the result is that it gives you an extra exponent in the log n. Okay, so Sham remembers, and the rest of you can pretend you remember. Let's do this. Let's do merging. We're going to do merging in linear time. And I'm not going to write the code, because you can find the code in that assignment for how computers work, and you could probably write it yourselves. But I'm going to describe it this way. We have 2, I'll call them pointers, but they're just integer indices into these arrays. They start at the first value of each array. And you compare these 2. And whichever one is smaller will go into a new array over here. That will be the sorted array when we're all done. Which one is smaller? You don't have any excuse to be slow and dense like I do. All right, so now 3 is gone, and we move the pointer down. Repeat. Compare where the two indices are. Come on. Okay, what happens when they all get run out of one list? When one list is done, you get out of that loop. You leave that loop. You break. If you look at the code, I'm pretty sure there's a break in that loop that gets you out. Then you go to a new loop that remembers which array was emptied before, and you go to the other array and you copy from wherever you were up to in the other array to the end. And you copy it over here. So you get 82. That's merge sort. Notice that it was completely important for us to have this fresh space. This is not an in-place sort. It's the first sort we did that isn't in place. We needed to copy it over to this fresh area because we couldn't move these things back to here because we might have needed things in the places that we were moving them to. It's like cleaning your desk. If your desk gets too messy, you need another desk to help you clean it up. All right. No. All right. How long does this merging step take? Every time you do a comparison, what happens?
You get to advance down the list.
You get to advance down one of your indexes. Every single time you do a comparison, you advance one of your indices. How many times can you advance one of these indices before the loop breaks? It's, well, half your list, right? Once you're done with half your list, the loop breaks. That takes at most n over 2 comparisons. And then what's going to happen? What's the worst case in the rest?
Well, not necessarily.
Well, what if it's all like this? So it could be n minus 1, right? Like Sam said, right? So the worst case is really n minus 1. But it adds up, right? Because whatever you leave over, you got to copy over at the end. So it actually takes n steps, period. Either comparisons or copies. But no more. Certainly linear time. Merging is faster than sorting. It's a fast algorithm. And we get this recurrence equation, and we get an n log n result. Chris, yeah, question?
The copying over at the end, is each copy not treated as a full action? You know what I mean? Like, do you gain anything by being able to just copy that over as a chunk? Somehow, like, there's 1,000 numbers left on the end, and you've already finished one of your halves. Is that still 1,000 times?
In merge sort, you really copy them. You don't just make a link over to the rest of it. You really copy it, yeah. But again, it would just make a difference as far as the constant factor, because it always takes n over 2 at least to get through it.
But in a typical implementation, it doesn't actually, you don't gain anything by having one list be
Right. You don't.
different orders. Okay.
So where's merge sort useful? Since it uses all this extra space, you got to realize that it's using this extra space at every level of the recursion. So at the lowest level, what actually happens here when you run this? When you run it, the first things that get compared are pairs of numbers at the very bottom, or lists of 2. They get merged and recopied. Then lists of 4 get merged and recopied. Then those 2 lists of 4 into a list of 8 gets merged and recopied. So you actually only need an extra n space, because at any level, you're either using 4 pairs or 2 things of 4 or 1 thing of 8. But you can reuse it as you go from level to level in your stack. So you don't need lots and lots of extra space, but just this much extra space. So it takes this extra space, and because of that, it slows it down, and it's not the fastest n log n sort, but it's useful for particular kinds of applications. And I mentioned this in the notes, but you should realize that it's useful. One of the things that merge sort is helpful to do is, since it's based on merging, merging is something that can really be done well when the data is stored offline. If you have data coming in on tapes or on relatively slow medium, you can actually merge them as they come in. So what if you have so much data that it doesn't fit in your RAM? You actually can't get them in an array. So merge sort is a wonderful way to do this, because you can sort pieces of it, throw it out on a disk, and then merge them as they come back in, and get them back on the disk like that. So you can pull them off the disk, process them, throw them back on the disk, without being able to have all this stuff in RAM at the same time. Nowadays, RAMs are huge. In the old days, this was like more useful, because you really had to do stuff like this. I'm not sure if there are data sizes that are so big you can't get them into RAM, but there must be.
When we had that guest lecturer come in and talk about how merge sort can break up into groups of
Heap sort.
Okay.
We're getting to that next topic.
Okay.
Yeah, what about it? But
Could you just? You seem to maybe be barking up your baloney tree.
barking up my baloney tree. Well, actually, we're going to get to heap sort and talk about what that guest speaker talked about. What he actually talked about is a legitimate topic, but he made it seem a little hocus pocusy, a little like, anybody ever read Marilyn Vos Savant's column in Parade magazine? It's like, it's never really wrong, but it really gives you the wrong impression of mathematics sometimes. It makes it seem magical and that you have to be a genius to understand basic things. And well, anyway, his talk was a little along those lines. What he said was actually kind of right, but he didn't give you any reason to believe him. Heap sort is based on a heap that works in a binary way, and he was talking about having it work in 3 children or 4 children, have what's called a D-heap. A D-heap is a well-known data structure. There's been a lot of work on discussing D-heaps versus binary heaps and what value of D is the best. And actually in the notes, if you look through them later on, there's an algorithm where I give you a reference just for that. And there's actually a problem in the book that talks about D-heaps that asks you to basically reconstruct that reference. And it's an optional problem on this problem set. And I'll talk about it later when we get up to it in a few minutes. I'll give you something quick. It turns out that, I've got to remember this exactly, but if you're doing a problem on graphs and you're using a heap to help you with your problem, that the best D for that heap is the number of edges in the graph divided by the number of vertices in the graph. Whatever that number turns out to be the most efficient number of children for your heap. And there are results like this, but we're getting way ahead of ourselves, so nobody knows what a heap is. Let's talk about that. Okay, next n log n sort, heap sort. A question so far before I move on to heap sort? Yes.
Maybe a really minor point, but I don't fully understand how this stuff will work off disk.
Yeah.
Because at the final stage, when you've got your n/2 arrays, and are you saying that
they're not n over 2 arrays? They're sitting out on disk somewhere.
When you don't read the whole array in at all, you're just going in, and wouldn't it be computationally very expensive to go in and read off an individual element in an array from a disk and then come and do it and then go back?
Yes, but there's no way to do it at all.
Right.
Yes, it's slow. It's slow relative to having it in RAM, but none of the other sorts could do it at all.
Okay.
Yes. So it's a good question.
I don't know how to break it down into each half if we haven't read the whole thing. If it's all off.
Well, usually the file structure will tell you how big it is.
Okay.
So, and you're just doing halves. So you begin by reading pairs of 2 and then throwing them back out. And then you do pairs of 4 and throw them back out. The recursion goes all the way down to the bottom before it starts backing up. So basically it starts with 2 and doubles it each time until it makes it up to the size of the actual list, which should be given to you as the first.
So we would have to read it from disk log n times?
Yes. Yeah. Yeah. Exactly. Other questions?
If it's a recursive process like the last one, does it always have to use extra space?
No. No, you can have recursive processes that are in place. The reason this process is not in place is not because it's recursive. It's because it does the copying. Quicksort is recursive, but does its work in place. It has a stack which has some information stored, but that information is not proportional to the size of the list. That information is proportional typically to the log n of the list. So it's a little bit not in place, but only by a log factor, not a whole linear factor.
So if there's a space constraint, it doesn't mean recursive processes are out.
Not necessarily, right. Right. Okay, heap sort is by far the most complicated sort we've talked about up till now. So I want to go through this a little more slowly and gradually. I will finish with this today. I may get up to quicksort. If I don't, what's coming up is quicksort, bucket sort, radix sort, and some other discussions. And then we're going to move on from sorting, shift over to searching and binary search trees and things like that. That's where we're headed. So let's talk about heap sort. Heap sort uses a very, very commonly used data structure called a heap. It's really important that you don't confuse the data structure heap with another computer science use of the word heap that means something completely different. Now, if you don't know this other use of the word, then why am I confusing you? But you might know it. So if you do know it, I want to make sure you know both and you can distinguish between the two. In a programming language that allows dynamic allocation of memory, which is almost any modern programming language, there has to be a way of saying, give me a new piece of information. Give me a new object dynamically. Let my array grow dynamically. Construct this new list and scheme dynamically. Now, when you do that, the operating system needs to keep track of where those empty spaces are coming from. And it typically has what a programmer will call a heap. All that really is a big, long linked list of free possible places. And when you say, give me one, it pulls one off for you from the top of that linked list. And when it puts them back, it frees memory that you're not using anymore. It puts them back onto this linked list. So it's a big heap. It's called a heap, but a heap in the sense of a whole bunch of. Okay? And it's typically stored as a linked list, although it can be stored in other ways too. But that kind of heap has nothing to do with this data structure heap. This data structure heap is a particular way of storing numbers in a particular order, and it's a different idea. Teresa, do you have a question?
I was going to ask where a linked list is. It sounds like you
well.
It's already been mentioned like 5 times today.
Oh yeah, linked lists are important. Mark will tell you what a linked list is. Right, Mark?
Sure.
Yeah, which day are we going to do that? 2 days from now, maybe?
Yeah, it's on Monday.
Oh, okay.
Monday? Okay. Yeah. Oh, but you know what a linked list is? It's for the most part, the lists in scheme were linked lists.
I think I'll ask Mike.
Okay. Or Chris. All right. Linked lists are very important, and you'll get to them soon. Heaps. What are heaps? The good thing about heaps is that the underlying storage of a heap can be done in an array. But the semantic and conceptual notion of a heap is in a binary tree. So the underlying thing will be familiar to you, but the conceptual approach is something you need to think about. So here is an example of a heap. A heap is a binary tree-like structure which is as complete as possible. If I add new elements into this heap, they will go on the next level from left to right. This will never become unbalanced. This will be completely wide, stable, and filled to the max. In this case, the whole bottom level is filled. If I added on another one, it would look like this. And furthermore, so this is also a heap. As long as it's a binary tree and filled up to the point that we can possibly fill up the level. The other thing that makes a heap, and you might be able to guess it from looking at it, is that the children of the parents are smaller than their parents. Just like with humans, up until they get to hit adolescence. But these are all preteen numbers, as you can see. So the 12 and 13 are smaller than 15, 11 and 3 are smaller than 13, etc. Okay. That's a heap. What's a heap good for? I'm asking you. What can you do with a heap? Forget, I know you can sort. You don't know how to do it yet. But what can you do with a heap besides sorting? What's a good thing to use a heap for? I threw a bunch of numbers in this heap, and here it is. You know what the highest number, getting the maximum value, right? Where is it? It's sitting at the root. We haven't decided how we're going to store this heap yet. I mean, we could store it with pointers, with left and right nodes. We could store it with parent pointers. There's a lot of ways to store a tree. Mark will talk about ways to store trees, review them with you at some point. But right now, we're not going to store this in a tree. We're going to store it in an array. And here's what it's going to look like. This will be the first spot, the second, the third, fourth, fifth, sixth, seventh, 8, 9, 10, 11. It would look like this in an array. 15, 13, 12, 3, 11, 6, 8. 1, 2, 9, 7. That's what the array looks like that stores this heap. This kind of an ordering of a binary tree is called level ordering. If I gave you a binary tree actually stored with left and right pointers and asked you to put it into an array like this, you could do it using a queue data structure. You would put 15 in the queue, you would take its children, put them in the queue, and then keep deleting from the queue, putting the children at the back of the queue. And what would happen is you would end up getting this exact order. 15 would come out first, its children would come out next, their children go on line behind. So you can get from a regular pointered representation of a binary tree to an array representation. But we're starting with the array representation. We have the level order version of this tree. It's one way to represent a tree. So where is the maximum? If we said we have a heap of numbers and I want the maximum, where is it? It's sitting at the root of the tree. As far as the array is concerned, it's sitting at the first slot of the array. So it takes one step to return the maximum. All right, let's think of what else a heap can do. It can get the maximum. That takes one step. There's other things you'd like to do in a heap. You'd like to be able to add numbers to it. I added some numbers. I got really lucky. I added 1, 2, 9, 7. They happen to fit right in where they're supposed to. What if I put in 10? Well, it's not a heap anymore. Insert. You got to be able to insert things in a heap. How long does it take to insert something in a heap? Well, let's do the obvious thing. We'll stick it at the end of the array. But now we've got to fix the heap. Fixing the heap is the most important thing to understand about a heap. If you can fix a heap, then you can add things to it, you can delete things from it, you can find out the max, and you can change the value of something in a heap and then fix it. We're going to do all those things. So let's say we add something to it. How do we fix it? We have to go ahead and basically bubble this 10 back up into its proper spot. 10 is bigger than 6. That's no good. So let's bubble it up. 10, 8, and 12. Is that okay? Is that a good relationship? That's fine. So we're done. What if this wasn't a good relationship? We would have to exchange these two. Exchange those two. We'd have to be able to bubble our way back up and put it in the right spot, exchanging elements as we go. What's the worst amount of time this can take? Log n, because the tree is as bushy as possible. So the height of the tree is log base 2 of n, where n is the number of elements in the tree. So inserting takes log n.
So does it matter at all whether the branches are at all balanced in terms of size of numbers? I mean,
no.
We have all our large numbers on one branch.
No, it doesn't matter. No, it doesn't. As long as they're balanced in level order here. Let's say I go in now and change this value. This value is no longer an 11. When might this happen? Let's say this is a representation of all the people who are standing in line at a bakery. You know, you stand in a bakery for 45 minutes because you go once every 3 months to a bakery, because who the heck goes to bakeries when you're so busy? You know, but there are other people who go to bakeries every single day, and they know the protocol. So they're sitting there with their numbers, and they know all the people personally behind the scenes, and you're waiting for a half an hour, and you're beginning to think, somebody's passing me by. And then you notice there's this funny little machine in a corner, and you're supposed to take a number. And everybody's been calling numbers, and you never had one. So, whatever. These are the numbers. These are the numbers in your tree. Let's say your number is 11. You're waiting and waiting. 15's next, 13's next, 12 is next, 11's next, right? But you are in a big rush. So you go over to the person who has 13, and you give them $10, and you say, give me your number. Just give me that number. Here's $10. And then they say they're really suspicious, but you just grab the number, you hand them the $10. They film like a Seinfeld episode while they're doing it, so like you can get some money out of it. And there you go, something about nothing. This becomes 13. Let's leave it. Yeah. Let's do it this way. Let's say you get a real person who's standing in the corner who's got 16 who didn't use their number. You changed your, forget switching. You changed your 11 to 16. It's not a heap anymore. How do you fix your heap? 16, 13. 13 comes down. 16 goes up. 16, 15, 12. 15 goes down. 16 goes up. You can always fix your heap.
But you also have to worry about whether you have to bubble down.
Yeah, you don't know what's wrong with it, right? So you have to
You
do
could change from 13 to 16 instead of, you could change from 13 to 2.
Good. Let's do that. Let's put it back at some legitimate heap value. Make this 13, make this back at 15. This is still a heap here, right? 10, 6, good. Now let's say this happens. 15 gets called. 15. All you want is a cupcake. All right. And let's say a new person comes in and they got a really teeny number and we want to insert them in the heap. 15's now gone.
Just this example is blowing my mind. There's no heap in the bakery.
There's a heap of cupcakes in the bakery. Let's say you take out 15. Let's say you take out the number 15. They're being served now. How do you fix this heap now? We took out the root. It's a big mess. Here's what you typically do. You take the one at the end, the 6. You shift it over here. That's a one-step operation. That's moving the back one all the way here, all the way to the front. And now you fix the heap by pushing it downward instead of bubbling it upward. Just what you asked for a second ago. So depending on whether you're inserting or deleting or changing, you might push your thing down or you might push your thing up. Either way, it's fixing the heap. How do we do it now? Now it's a little harder than before, but not too much. Now you can't just compare the value to its parent and do a swap, which is what we did when we were pushing up. When we're pushing down, we have to look at both children, because we want the bigger one to take the place. So this takes an extra comparison or so at each level, but that's all. 13 is the bigger of 13 and 12, and 6 is smaller than both of them. So 13 moves up here, and 6 comes down here. 6, 3, 11. What happens there? Agreed? 11 moves up, 6 comes down. 6, 7, 9. And now we have a heap again. So you can either push your value down or you can push your value up. And whatever direction you push it, it's order log n. 1 second, Rob. I'm just going to write deleting takes order log n. Inserting takes order log n. Changing a value, order log n. What a nice data structure. How balanced. We always move the one that's at the right up to the top.
Right.
So we took it off from the...
If you moved it up at the top and it became a child of the 8 that's in the bottom right, then you'd have a hole in your bottom line of leaves.
Can't do that.
I think he's saying that's just 13 is where the 12.
Oh, you're never gonna you never actually add a new edge to your tree when you do this. You're just switching values of things that are already there. So if it did end up going down here, the worst that would happen is that it would take the place of an 8, but it would never become the child of an 8. Do you get it?
Yep.
Yeah, it's a good question, but it won't happen. If it did happen, we'd be in big trouble. Yeah. Yeah.
Does the bubbling up thing that you talked about first, does that ever actually happen in a heap? Is that...
It happens, but it doesn't happen in heap sort. It happens in other uses of a heap.
You have to do, someone might have said this, I don't know, but you have to do a little check back down to your, after you get promoted, a check back down to both of your children? Because couldn't you be larger than the 12 but smaller than the 12s?
I don't think so, because this, assuming it was already a heap on top, this has to be bigger than the other child.
Say that's a 15, or say it's a 15 on top and a 14 over there on the left.
15, 14,
And a 12 over there.
12.
And say you're a 13 bubbling up on the right. You swap the 12, and you're done.
Yeah. I don't think that happens because the one on top is guaranteed to be in the right place relative to the other child. But on the way down, you do have to check both. So I don't think you need to do a check back on the way up. Other questions before we go on about this? So I want to say a couple things about heaps before I talk about heap sort. You've seen how to fix a heap going up and down. You've seen that it takes log n to insert, log n to delete, log n to change. This is a great data structure. It's perfect to use for what you did in your Java course assignment 1. You guys did a priority queue, right? This is perfect for a priority queue. You want to get the next one online? Get the max. You want to put a new person in? Insert. You want to take a person out of the queue? Delete that person. You want to change the priority of a person who's already in the queue? Change it. Now let's go ahead and pretend we did a priority queue in a much simpler way and compare it to this. We'll do it with two very obvious ways, an unsorted array and a sorted array. Sorted array. Let's say we were going to keep an unsorted array of our elements. How long would it take to get the max? N. How long would it take to insert? Constant time. How long would it take to delete? You'd have to find it, and then you'd have to collapse it. How long would it take to change something? You'd have to find it and then change it. Let's say a sorted array. It's all sorted now. How long does it take to get the max? 1 step. How long does it take to do an insertion? You can find it in binary log n time by binary search, but you got to shift it. So it takes n. How long does it take to delete it? Still got to find it.
Sorted, can't you do it binarily?
But you still have to collapse it back down
Oh, that's true.
to keep it even. Well, we could just say leave blanks, and then we could have this be log n. And to change it, same thing, order n. Look at how unbalanced this is. Everything's n's, but you get one thing that gets to be constant. Here, everything's perfectly balanced. Insertions, deletions, and changing. And they're all pretty fast. That's why this is such a commonly used data structure. It's really, really worthwhile. Mike, is there something I missed here?
Well, it has the same balance as the sorted array. I mean, they're n, but they're balanced.
Yeah, well, this one's a little better than this, right?
Well, the difference between constant and log n is smaller than the difference between constant and
Okay, agreed. So it's not the balancing that's so great. It's just it's that the complexity's better. I'll go for that.
It's probably just a constant time issue of, we still have the same problem. We have to find, deleting, we have to find and we have to bubble, which would be, but it would just be 2 log n, so it won't make
Exactly.
sense.
Exactly, right. How do we do this fixing of a heap? We're not going to write the code, because the code is basically a loop that goes up and down this tree. But there's one basic operation at the lowest level in that loop that you have to be able to do. Otherwise, this just becomes too abstract relative to the array. And that operation that you have to be able to do is saying, look, if I'm at this spot, how do I compare this to its 2 children? How do I compare this to its parent? Those are the things that you need to be able to do. So if I give you a spot, how is it represented? In the array, it's an index. I give you index j. Where are the children in the array? Where are the parents in the array? Everyone understand the question? You got to be able to know how to do this. Otherwise, the link between this implementation and this abstract data structure is too great to gap. You have to bridge that gap by knowing how to take an index of the value and finding its parent and finding its 2 children. How do you do it?
You write it in binary code. You write the index in binary code.
Well, that's a little too much work. It's the right idea, but we don't have to even do that much. Let's write it out.
Divide by 2, multiply by 2, multiply by 2 plus 1.
I'm writing out the indices of these values.
Parent is going to be the greatest integer in n over 3.
So let's look at the children first. It's not an accident we store it in level order. The reason we store it in level order is not just because it makes sense. We like things in a row at a time. We do it that way specifically because what we use in a heap is the specific need to go from parent to child and child to parent. And in this level ordering, the indices relate in a very nice way. The children of a particular index, for example 3, are double that child and double that child plus 1. So j is connected to 2j and 2j plus 1. If you're given a particular index and you want to know its parent, it's just half that parent. What if it's an odd number? Then it's half that parent but round down. Floor of half that parent. So going upward, you do the floor of that index divided by 2. Going downward, you multiply by 2 to go to the left, and you multiply by 2 plus and add 1 to go to the right. Then you can code anything you need to do on a heap. That information is very important. Now, I didn't prove this, okay? If it were a discrete math class, we would prove that this is the case. And how do you prove it? You can prove it by induction. It's very nice to be able to prove it. We're not going to prove it. If you want to prove it, go ahead and do it, and it's interesting. And you can all see that it's true. If it weren't true, then it'd be more important to prove. Okay, a little bit more, about 10 more minutes we have. I don't want to have, forget it. 4A, 4B, what the heck. Here's a heap. Let's talk about how to do sorting in a heap. Once you understand a heap, sorting with a heap is very straightforward. The only question is how to get the damn data to be in a heap to begin with. We'll talk about that at the very end. So let's assume the data is given to us in a heap. It won't be in general. But we've gotten it into a heap, and hopefully that won't take n squared time. We can do it quick, get it into a heap, and now let's go ahead and sort it. Well, here's what we're going to do. We're going to sort it the normal way in ascending order. So we want the smallest guy to be here, second smallest here, third smallest, and the biggest one to be at the end. Okay, here's the idea. What does a heap give you? It gives you automatically the biggest, the maximum. Where does the biggest belong? The biggest belongs at the end. So you have this in an array. You take the first value in your heap. You exchange it with the last value in your array where that value belongs. And now, in your mind, you make a little mark here. This part of the array is sorted. The bottom of the array. The last value is sorted. And now you no longer have a heap. This is now out of the heap. Okay, the heap only goes up till here. This is our storage area. We're keeping this sorted. We're sharing this heap space, this array space, part of which is a heap. Up to here is still going to be a heap. And this part and everything past it is the area that we never look at again. All right? It's a little tricky. We do that to do it in place, not to have to move it to a new place. Yeah?
If it's only that bottom corner at this stage, wouldn't the 4 be at the top and the 2 be where the 4 is?
Yes, if we would fix this. Well, maybe I'm missing your question.
Well, as the 15 would swap with the 4.
No. What we do here, we just go ahead and swap the first and the last. We haven't fixed anything. We are consciously knowing that we are messing the heap up big time by doing this. But we've got the biggest one in the right spot. What do you do with a 2? You push it down just like we did when we deleted an element. This is essentially deleting the top one from the heap, but where do we put it? Instead of throwing it out in the trash, we throw it at the end because we don't need the end spot anymore. We'll just move that value that was there back up to the top of the heap. And now we fix the heap by pushing that down. Chris asked, do we ever actually push things up in heap sort? And the answer is no. We do push things up in heaps when we use them for other applications. But in heap sort, we actually only push things down. So we're going to push this 2 down. What does it look like when we're all done? Well, bit by bit. 7 switches with 2, right? 4B switches with what's the chance this sort is going to be stable? Stable means equal size elements stay in their same order. I'd like to point out that 4b used to be after 4a, and now 4b is before 4a. That's a bad sign. Maybe it'll get fixed later, but I doubt it, and you should doubt it too. Heap sort is not good if you want a stable sort. Because of this beautiful tree structure, it can't do everything.
What are we going to do after we take the 7 out? Which of 4A or 4B is larger?
Depends on how we implemented it, whether it was less than or equal or greater than or equal. But the point is, whichever way we did it, we couldn't have known in advance which one of these came from lower in the tree or before. So whichever way we did it, it could do it wrong. We'll just do it randomly. What's next in heap sort? We just did step 1. 7's the next biggest, so swap it with the next. So we're going to need an index that remembers this spot, this next open spot, or the last legal spot of the heap. Okay, the heap is in an array. The array will have a length. This is why Java sometimes is a little rotten for this, right? In Java, you have a length of your array. It's all the legal spots in your array, right? So you're going to have another field in your object, or maybe something that inherits this, that adds in, I've got my length that goes all the way up to this value, but I've got my heap length that goes up to this value. You just got to be careful to get it all right. If you were just using C, you set yourself up an array, you keep all the indices you want, and you won't mess anything up. More flexibility, less structure. Less structure. Now this is sorted. Now we have to fix it again. We'll randomly choose between 4b and 4a. I don't care. Let's do it this way. 4b will come up. 1 will go here. 3 will come up. 1 will go down here. We fix the heap again. We're ready to switch 4b with 2. Yes?
What if that 7 had been on the other side of the tree? Then if you had gone down this side, then you would have... I'm just wondering if there's...
You wouldn't have gone down that side. You would pick whichever side is bigger.
Oh, okay. So the way you're choosing which side to go down is by seeing which number is bigger.
Exactly.
Oh.
Right. We never mess up the heap that way. Right. Let's do it right now. We have to push 2 down. Which side is it going to go down? It's got to go down the bigger side, the 4a side.
Okay.
We always look at these two, pick their max, and put their max up here. Does that make sense? Oh, I did it randomly before because I had 2 4s, and I didn't know which way to go. Okay. Now we switch 4a with 1. One, was it? Yep. Okay. And now I have to push this down through a teeny heap.
Switch
3 and 1. Then I switched 3 with 2. So now this whole area is sorted. 2 and 1. I push 2 and 1 here. 2. And you're all done. All right. That's how heap sort works. Let's analyze it quickly without getting too hairy. Basically, you have n-1 iterations of some procedure. Right? We're doing this one at a time, n-1 times, till we get to the top. What happens each time? Each time, we do a constant swap to the lowest spot, and then we fix the heap. Fixing the heap is log n. We do n of these. It's n log n. That's very fuzzy. Why is that fuzzy?
log n's keep changing.
Right, because the depth changes, right? I mean, at the beginning it's log n to fix it, but later on it's smaller heaps. So you know what it really is? It's really this. Log n the first time. In fact, log n the first 4 times, and then log n minus 1 the next few. It's a complicated sum. All right? So go ahead and look at it and do the sum and go discrete math yourselves to death. When you're all done, it turns out that it's not n log n. It is that it's not faster than n log n. Just because you're getting shorter trees on the way up, it cuts it down by a constant factor, but no more than that. So your gut instinct of it being n log n processes is actually right.
Is that exactly analogous to the bubble sort going n minus 1 and n minus 2 but it's still n
It's,
squared.
it's a similar idea, but it's not exactly analogous mathematically. But it's similar. The thing is that something really similar to this does cut down the complexity. And that has to do with the very last thing I'm going to do, which is building a heap. So I want to talk about that. And since the rest of our process is taking n log n time, it better not take too long to build this heap. Ideally, we'd like it to be less than n log n. We'd like this to be not the main step, but maybe linear time. So we got to be able to figure out a way of taking an arbitrary array of numbers and turning them into a heap. All right, you have a big problem in the problem set on this. There's two ways to build a heap. Well, there's probably a lot more than that, but there's two obvious ways to try. And one is no good, because it takes n log n, and one is good because it takes n. I can describe both of them very briefly to you today, and then you will, in your discovery and working through that problem, flush out the details. But I want to at least give you a little bit of a head start on it and a heads up on how the two different ways work.
If it took n log n, it would still be n log n complexity, right?
That's true. But there's a lot of other uses of a heap where the use is less than n log n. And we can't do it at all if building the heap takes n log n. So you're 100% right, Chris, that in this particular application, well, who cares? The whole thing's n log n anyway. Why bother getting it down to n? But it's important because other applications use less than n log n. OK, let's say here's our numbers. 8, 3, 4, 6, 2, 5, 7, 9. I should really write this as a tree because you'll get a much better sense of what's happening. 8, 3, 4, 6, 2, 5, 7, 9. Here's one way to build a heap. I'm going to do this very abstractly, not discuss the recursive variations that are equivalent to it or the coding. Just how do you do it on the data? One way to do it is to work from the top to the bottom, building the heap one element at a time from the first element to the last element. Here's what I mean. That's a heap all on its own. We're OK. The first element by itself is a heap. Now I'm going to introduce the second element and try to include it in the heap. This is similar to insertion sort, giving me more and more of a sorted area in my array as I go. So now I'm including 3. I would like to include this and make this a heap. What do I have to do? I have to focus on the 3. And what do I have to do with that 3? I need to bubble it. Which direction? Up, right? This time we're going up. So I got to bubble it upwards in the heap. And I end up getting just what I have. Thank you. I was just about to change it by mistake. 8, 3. Good. So it's already a heap. Super. Now I go to 4. I try to bubble it up. No problemo. I got 8, 3, 4. Now I go to 6. That is a problem. I have to move it up, right? The 6 switches with the 3, and the 6 doesn't have to switch with the 8. Does everybody see the idea? I don't have to go through the whole thing. You go one at a time, you let them bubble up. This is funny because there's two directions here. You're going top down, but the elements are bubbling from the bottom up. Okay? So sometimes say, which way is top down, which way is bottom up? Because the other way that I'm going to tell you right now starts from the bottom up, and the elements bubble top down. So whatever you want to call either one, just know which one you're talking about. Here's one way. The next way works like this. We'll start with the same list. 8, 3, 4, 6, 2, 5, 7, 9. And this way works from the bottom up. 9 is a heap all by itself. We'll include 7. 7's a heap all by itself. The leaves are heaps all by themselves. Now 6. To include this, what do you have to do to 6? You have to push it downwards and switch it with 9. Now you go to this one. 4 you want to include in the heap. How do you include this one? You have to push it down, switching it with 7. Now you want to include 3. And all the things below you are heaps already. So you're just trying to push your non-heap things down and make your heap grow upwards. 3 with 9 and 2. 9 takes the place of 3, and you have to keep going, right? You have to push 3 all the way down. 3 takes the place of 6. Uh-oh, what goes here? 3. Now I got the last one, 8, 9, and 7. 9 goes here, 8 goes here, 8, 6, and 2 doesn't have to move any further. Okay. One of these ways can be done recursively in one fashion. One of these ways can be done recursively in another fashion. You get 2 different recurrence equations. One of these ways is fast, one of these ways is slow. Without coming up with a recurrence equation and solving it and figuring it out and going back to all the math, you'll have to do that. You'll have plenty of time to think about it. Now you've got exactly 3 minutes to think about it. Just based on this description, intuitively, which way do you think is faster? Pushing down is faster? That means this second one?
No.
The first one? The first one we're going from top to bottom, but we're pushing up. The second one we're going from bottom to top and pushing down. So it's better to push the elements down or better to push the elements up? Push the elements up. Up. Now we have a consensus. Down, up.
Down.
Fewer elements.
We're misstable because I vote right.
Yeah, the tree doesn't have equal elements in the second.
I would yield in a second.
This represents how many elements are at each level of the tree. Okay? I'm going to write time to fix an element. We got 2 choices. Pushing up, pushing down. Okay. If we're pushing our elements down, that means the second one. How long does it take to push an element down when it's at this very first level? 4 steps, right? How many here? 3 steps, 2 steps, 1 step, 0 steps. Right? The bottom ones take 0 steps. If we're pushing the elements upwards, then if you're at the root, it takes 0, 1, 2, 3, and the bottom ones. What would you like to do? Would you like the time it takes to fix the elements to be higher, where you have very few elements? Or do you want them to be higher, where you have a whole bunch of elements? You want it to be higher, where you have few elements. You want it to be lower, where you have a whole bunch of elements. There's this very nice balance in this one. You got 16, but it doesn't cost you squat. You got 8, it costs you a little bit. You got 4, it costs you a little more. You have 1, that costs you the most. What is this? This is log n times 1. Log n minus 1 times 2. Log n minus 2 times 2 squared. Log n minus 3 times 2 cubed. You get a big, long summation. You add it all up. If you add this all up, all the way from 1 to 2 to the n, where 2 to the n is the number of values in your whole list, you're going to get order n. I said that wrong, but you know what I mean. Well, maybe you don't. If you add this all up in a summation, you'll get order n. But if you add this one up, where you don't have this beautiful balance, what happens at the bottom is pretty much what happens throughout. You have log n at the bottom. You've got n over 2 of your vertices here already. Just the bottom line itself is already n over 2 log n. Just the bottom line itself should scream to you that this stuff is not going to do any better for you. You're still going to get order n log n. So now I've given you the intuition on this, I think, a nice way of looking at it as to why one way is better than the other. But there's a lot more to do on this problem. There's a lot, and I'm going to actually, I think I asked you to actually code this. So you're going to be forced to understand it. If you think you understand it now, you'll really have to understand it later. All right, final questions, then we'll quit. We'll do quick sort, radix sort, bucket sort tomorrow. Any questions?